Welcome to another video on implementing preference heterogeneity in discrete choice models. Our last video discussed identification and emphasized that we need to think clearly about identification issues and possibly leverage panel data or other hierarchical structures in our data to be able to plausibly identify preference heterogeneity. In this video, we'll move from identification to estimation. We'll formally introduce what the likelihood function looks like for the mixed Logit model. And the key takeaway is that we're going to find that we have an extra integral in our likelihood function that can't be mathematically derived away like we could for the extreme value type 1 errors in the Logit model. And so that's going to require us to learn a little bit more computational tools, and we'll cover those briefly in this video as well. Let's go back to our prototypical utility function where we have x beta and z gamma and epsilon. In this case, we're allowing z to also vary across individuals. Now, this would not always be the case. If z is the price and there's no price discrimination in the market, then everybody's paying the same price. But we could think of z as being like travel time between my home and my work. And that's going to be different for every person because not everyone lives and works in exactly the same place. And in this example, let's just mix over the gamma parameter. So this is going to mean that gamma I is drawn from some distribution f with PDF lowercase f. And then it has distributional parameters mu and sigma that we're going to need to estimate as well. Under these assumptions, and given that epsilon is type 1 extreme value, IID, then we're going to get mixed Logit choice probabilities that are going to be a function of gamma I, but gamma I is unobservable, and so we're going to need to integrate it out according to its PDF little f. So our parameters now are beta, mu, and sigma instead of just beta and gamma. So we have one additional parameter to estimate, which is the standard deviation of the distribution that gamma I is drawn from. And then we have our data x and z, just like we always do. So why do we set up this integral in this way? Well, if you remember from an intro stats class or an intermediate stats class, the expected value of a function of a random variable is the integral of g of w times the PDF of w dw. So that's just the definition of an expected value of a function of a random variable. And so in this case, the function of the random variable is going to be the Logit probability formula. And then we have to tack on this density function and then integrate it out. So now if we think about the log likelihood for this model, this is going to be much less tractable because we can't pass the log through the integral in general. So we have our beta, mu, and sigma. There's a typo on this slide. That gamma should not be there. It should be mu and sigma. And basically, instead of being able to pass the log through the product over the j's, we have to take the product over the j's before we do the integral. And we also have to evaluate this exponentiated dummy variable as well. So the whole thing just becomes very intractable because we have the product over all of these different pj's. And we can't, in general, switch the order of the integral in the product. So that's our log likelihood function. And we can't just go about our merry way and use basic nonlinear optimization packages like we're used to because we have to figure out how to handle this integral. But before we talk about how we can do that, let's think about other mixing distributions out there. So the normal distribution is a natural place to start. Why? Because everybody loves the normal distribution. Its properties assume that there is a lot of mass around the center, and then in the tails is very small mass. So this type of distribution would assume that most people have very similar tastes, and then any kind of aberrations from that are quite minimal. But we could instead have a log normal distribution, which would imply that there's quite a bit of a tail to it and quite a bit of density in the tail compared to the normal distribution. We could assume a uniform distribution, which just means that at any given level of taste, there's an equal share of the population that falls in that category. We could have triangular, which is similar to normal, except there's going to be no mass after a certain point. And then with the triangular, this might be easier to compute the integral of compared to the normal distribution. We could also specify a multivariate normal where we have multiple random coefficients that are correlated with each other. So in general, if we go back to our formula, we would just have, suppose that we were also mixing beta as well as gamma. We would normally just assume that those are independent distributions, but there could be some correlation between how much I value the price and how much was my household income, for example, or whatever. So if we did that, then we could use the multivariate normal, which would allow for the unobserved preference heterogeneity to be correlated across the two random coefficients. Of course, if we want to do that, we're going to have to think about, can we plausibly identify that degree of heterogeneity before we go and start estimating it. So now that we think back to this likelihood function that I showed you, solving that integral is going to be fairly intensive from a computational standpoint. And what we're going to have to do is we're going to have to numerically approximate that integral in order to get it out of our likelihood function. And there's several ways we could do this. The most common way, especially if it's a single dimensional integral, would be using quadrature. Another common way is to use some sort of simulation-based method, which in this case would be called Monte Carlo integration. And I'll go over both of these momentarily. How do you know if you should use quadrature or Monte Carlo simulation? Well, the answer is problem specific, and so I don't know of any rule of thumb, but typically if it's 2 or 3 dimensional integral or lower, then use quadrature. Otherwise, use Monte Carlo integration, but it's honestly up to you. So let's talk about quadrature. And let's harken back to our intro calculus class where we first learned about what an integral was. And at least when I was taught it, we talked about Riemann sums, and taking the limit of a Riemann sum approximates the integral. So as the Riemann sum has more and more of these bars that you see on the screen that become infinitesimally small, then it approaches what the integral is doing. So that's basically what we need to do. We need to approximate this integral over the gammas according to this Riemann sum with these bars that you see here. So formally, the integral of f times d gamma is approximated by some summation of weights times the function evaluated at the grid points. So we call the gammas our grid points, and then the weights are like how thick the rectangle is. And there's also other implementations where you use the trapezoid rule instead of rectangles, because that will give you less approximation error. There's also something called Simpson's rule. There's different ways of doing this, and you can look at a calculus textbook if you're interested about that. For the time being, we're sort of approximating d gamma with this grid weight, and then the f we're also just evaluating at the grid point. So with a Riemann sum, we have the same just delta gamma for our weights, like I was saying. For quadrature, I don't want to get too far into it in this video, but we can come up with optimal weights that will allow us to use many fewer grid points. And these weights are not going to be uniform, but they are going to be derived for accuracy. So this problem of quadrature is not something that is limited to integrating out a likelihood function. There's other applications of quadrature in other branches of science and math. And so those tried and true quadrature methods have been developed in those other fields, and then we can just kind of port them over into our econometrics. So that's the basic idea of quadrature. Now, what about Monte Carlo integration? Well, Monte Carlo integration says I'm just going to randomly sample from the support of f according to its distribution. So these red dots are random samples, and we're sort of showing how likely they are based on the density of our f. And then I'm just going to take every one of those samples, I'm going to give it equal weight, in this case 1 over r, where r is the number of samples I've taken. And then I'm just going to sum the value of the objective function or the PDF that we're trying to integrate over, and I'm going to just do that to approximate the integral. So with Monte Carlo integration, we're having uniform weights of 1 over r for all of our draws, and we're just going to draw some number from the support of our distribution, and then just take the average across all those, and that's going to be our integral. And if r is very, very large, then this will converge to the correct integral value. So typically you need some very large number of r, like 10,000, at least 1,000, to get this to work. Whereas with Quadrature, sometimes you can get away with just 3 grid points, 7 grid points max, and that's usually enough to handle it. So in general, we would prefer to use Quadrature because it's just a lot easier in terms of managing the number of grid points, but Monte Carlo can also get us there, and we can, you could come up with coding examples that could show that. I'm not going to show that in this video, but maybe in another video at another time. So that's what we have for the estimation of the mixed logit model. As you can tell, once we implement these random coefficients, the estimation becomes much more difficult, but there are packages out there that automate this process, so we don't always have to be doing it by hand every time. But if we have a model that is atypical, then we might have to do it from scratch on our own. In the next video, we're going to talk about finite mixture models. This would be a situation where we assume that the distribution of the unobserved preference heterogeneity is finite or discrete, and we'll see how this can maybe help us to lighten the computational burden that has been placed on us by these random coefficients that are due to unobserved preference heterogeneity.